So here's a nice group called Sn, which is the symmetry group of the set 1, 2, 3, n minus 1, n. The set, a finite set of n elements. It's sometimes called the permutation group on n letters. Because an automorphism of this set just reassigns the places in line. And we saw that this is a finite group because there are only finitely many permutations of a set of n letters, and the order of it, that's the size of the set underlying the group, n factorial. I might write that this way. This is the way Artin would write that. The order of the symmetry group of Sn is n factorial, because there are n factorial ways to permute n letters. Why? Because there are n choices for the letter you take first. And then there are n minus 1 choices for the letter you take second. And then there are n minus 2 choices for the letter you take third. Okay, let's take a look at the symmetric group on a few small letters to get an idea how we would analyze it. So the simplest one is S1. S1 is a very simple group because the only permutation of a set of one element is the identity. So that's a famous group. That's the simplest group you can have, because any group has to contain an identity element, which happens to be its own inverse, and et cetera, et cetera, et cetera. So that's an easy group. It has one element in it. You can have a set with 0 elements, right? The empty set. But you can't have a group with 0 elements. Simplest group you have is one element. How about S2? Well, there's the identity map that takes, let's write our permutation like this. This would be the identity permutation. Takes 1 to 1 and 2 to 2. But there's another element in this group that takes 1 to 2 and takes 2 to 1. Let's call that permutation tau. Okay, so S2 is a set which has 2 elements in it, E and tau. Now, those are the only possible permutations of 2 letters. And we want to know what the multiplication law is. Well, if we compose any permutation with the identity permutation, we get itself. So obviously you have E tau is equal to tau E is equal to tau. And what about if I compose tau with tau? It's E. If I do this twice, so I take 1 to 2, then I take 2 to 1, it goes back to 1, and then I take 2 to 1, and I do it again, 1 goes to 2, so 2 goes to 2. So here I have this law. So in other words, tau in this group is equal to tau inverse, because it is the transformation that multiplies by tau to get E. So that's a pretty simple group. It has 2 elements in it, the identity and a non-identity element. And the non-identity element, when I multiply it by itself, I get back to E. So the multiplication table, if you really wanted to write this thing out, which I don't recommend ever doing, would look like this. Okay? Now that's an example of a group that I called last time abelian or commutative. So if AB is equal to BA for all pairs, say G is abelian or commutative. Some people capitalize abelian in honor of Abel, some people don't. Doesn't make any difference to me. So this group is commutative. Commutative group just means that the multiplication table is symmetric around the diagonal, and this one is. S3. So of course we have the identity element. That one we already knew about. Now we have an element like this tau. Namely, we can forget about the fact that we have 3 elements, leave the third element fixed, and just permute the first 2. Like that. Let's call that element tau. We've already seen that element. Now, elements in the symmetric, this is, by the way, called the symmetric group, or permutation group on n letters. Symmetric group on n letters. I'm sorry for all these different terminologies for the same thing, like automorphisms and symmetries. This kind of symmetries, where you only exchange 2 elements, well, that was obvious in this case, are called transpositions. So if you have a very simple type of permutation is to fix everything but two elements and just exchange those two. Those are called transpositions. They're very important, as we'll see later on in the theory of the symmetric group. Now, in this case, we have this transposition, but we also have some others. Can someone tell me some other transpositions in the symmetric group on three letters? Yeah? Right. So there are three different elements we could fix. Right? We could fix 3, but we could also fix 2. We could also fix 1. So there are actually 3 transpositions. I'll write them down. So we could fix 1 and switch 2 and 3. Let's call that one tau prime. Or we could exchange 1 and 3 and fix 2. Those are all 3 different. I could call that tau double prime. So far we've found 4 different permutations of the set of 3 elements. We ultimately have to find 3 factorial, which is 6. So there have to be 2 more permutations of 3 elements. So I'll write you down another one that isn't a transposition. If it's not a transposition, it can't fix anything because there are only 3 elements. So once it fixed 1 element, it would have to either fix them all or just exchange the other 2. We've already written down all of those. So let's write down something that doesn't fix anything. Well, we can take 1 to 2, and 2 to 3, and 3 back to 1. Let's call that one sigma. Or, another possibility, instead of taking 1 to 2, we could take 1 to 3, right? Then we could take 2, I guess it would have to go to 1, and 3 goes to 2. Let's call that one sigma prime. So we have 3 transpositions, the identity element, and these 2 elements that don't fix anything but represent different permutations. So those are the 6 elements of S3. E, tau, tau prime, tau double prime, sigma, sigma prime. Now, the fun starts. Let's see if we can find... Let's see what the composition of these things looks like. In particular, let's see if this group is commutative. So let us compute tau sigma, and let us then compute sigma tau. Now, how do you compute tau sigma? Well, you have to figure out what it is as a permutation of the set of 3 elements. So the first thing I'd want to know is what does it do to the element 1? Well, let's figure that out. This says, first, now this notation means first apply sigma to 1, and then apply tau to what sigma takes 1 to. So this becomes tau of sigma of 1. Sigma of 1 is, by definition, 2. Right? And tau of 2 is 1. So this becomes tau of 2, which becomes 1. So this permutation, whatever it does, it fixes 1. It fixes the element 1. Now I can tell you right away what it is. There are only 2 of these 6 permutations that fix the element 1. What are they? It could be E. So tau sigma is either E or tau prime. Now I claim that it isn't E. That I can tell you right away, without even thinking about it, by pure thought, that it is an E, without computing what it does to 2. Now, I could check by just seeing what it did to 2. Let's do that. That's the computational approach. Proof. Tau sigma of 2, well, we first compute sigma of 2. That's 3. It's tau of 3. And tau of 3 happens to be 3. So it's beginning to look much more like tau prime because it fixed 1 and it took 2 to 3. Now that says it has to take 3 to whatever's left because it's a bijection. So that immediately implies that tau sigma is equal to tau prime. That's our multiplication table we're starting to work out. But if I wanted to do it by pure thought, without ever computing what it did to 2, how do you think I could eliminate the fact that tau sigma could not be equal to E, given the fact that this is a group? Yeah, go ahead. Ah! They're clearly not inverses of each other. What is the inverse to tau? Tau. That's all you have to say. Inverses are unique. The only possible thing that when you multiply by tau, you get back to the identity is tau. Sigma doesn't look like tau. So, but you could also argue, very good, that the inverse of tau is equal to tau. By the way, what's the inverse of sigma? Can anyone tell me what the inverse of sigma is? What? Ah, very good. Sigma inverse is equal to sigma prime. If you look at it, if you want to get this back to where you started, you have to take 2 to 1, you have to take 1 to 3, and you have to take 3 to 2. That's what sigma prime is. So with these 6 elements, this is just the fun. You know, now you can start taking products and inverses. But in any case, we've computed that tau sigma is tau prime. We've got that. Let's now compute what sigma tau is. Well, we'll compute sigma tau by computing it on 1. Okay, we start off by tau of 1 is 2. So this is sigma of 2. And sigma of 2 is 3. So sigma tau of 1 is 3. Interesting. So there are 2 possibilities for it. It could be tau double prime, or it could be sigma prime. We're again down to 2 possibilities. Well, let's compute sigma tau of 2 just to kill the suspense of it all. Tau of 2 is 1, so this becomes sigma of 1. Sigma of 1 is 2. So it fixes 2, and therefore it's equal to tau double prime, right? So therefore sigma tau is equal to tau double prime. Here. Fixes 2, takes 1 to 3. And therefore, sigma tau is not equal to tau sigma. So already, in this incredibly simple permutation group on 3 elements, it's non-abelian. Okay?